everyone. Thank you so much for coming. As the guys were saying, today we'll be exploring how we are designing actually, a native account abstraction scheme for a private network. For those of you who were here yesterday for Jake City's talk from the WAX PSE team, this talk will have some similarities in the sense that we're using CK snarks for verifying transaction validity, but you'll see that when we enshrine that and make it a native part of the protocol, the implementation turns out to be something completely different. And that's what we'll be exploring today. So while we wait for the rest of the people to finish waking up and coming here, let's make the mandatory 2-minute intro on what account abstraction is. So account abstraction, in a nutshell, is allowing us to customize the validity conditions of a transaction. When I mean validity conditions, in Ethereum, we usually think about a valid ECDSA signature that points to an account that has enough funds to pay for the fees for that transaction. In account abstraction, we allow the user to customize that. So in other words, what we get is that the transaction is not just the business logic, the execution, the intent that the user wants to run, but also has code to indicate when the transaction is going to be valid. Why is that important? Because it allows us to break the link between user identity and private key. It allows us to implement whatever transaction signature methods we want, leveraging the cryptography of whatever devices we have handy, and also allows us to implement nice UX and security features, such as multi-factor authentication, key rotation, social recovery, daily withdrawal limit, you name it. Account abstraction also can serve as a building block for abstracting fee payments and allowing us for users to pay transactions in kind or to subsidize user transactions, which is something super, super important in the context of onboarding. Account abstraction then usually takes this shape. It breaks the transaction into two distinct phases: initial verification phase that defines, think it of a Boolean function that defines whether the transaction is valid or not, and also locks the fees for payments, an execution phase that carries the actual logic, the business logic. The important thing here is that the verification phase is what defines the validity of the transaction. So if a sequencer picks up the transaction, runs the validation, and gets a false out of it, that was work that it cannot get back. It cannot get reimbursed for that effort. So it's super important that the verification phase, it's easy to execute for a sequencer, and also that it's deterministic. Like, we don't want a verification phase that returns true when the sequencer picks up the transaction, but by the time it gets included, it returns false, and sequencer is screwed. So with this as a context, we'll see how we can leverage CK snarks to solve this problem. But first, let's talk very, very briefly about what I mean when I say about a private network, in particular, the Aztec network, which we're currently building. I'm talking about a private first layer 2, in which private state is represented with an UTXO-like model, and that executions happen client-side. In other words, a private transaction runs in the user's device and outputs a zero-knowledge proof, a snark, that proves the correct validity of it. So for instance, a simple private token transfer would look more or less like this, in which the user, pointer doesn't show anyway, in which the user requests a transfer on the token contract, and the token contract executes whatever logic it has, and outputs a series of data commitments, encrypted nodes, nullifiers to consume previous nodes, and the entire output of the transaction, basically what gets broadcasted into the network, is a CK snark of the correct execution along with that set of nodes, commitments, and nullifiers. And again, since execution happens locally, execution has access to a private execution oracle. Think of it as a piece of software that runs in the user's wallet, and that can help by providing access to local encrypted data, encryption keys, or whatever you need. And this private oracle is going to become handy in a minute. So now that we have the context of account abstraction and also what we mean when we talk about a private network, how can we bring these two together? Like, the first step we took is making sure that every single account in the Aztec network is a smart contract. So we have no concept of EOAs, which make developers' lives easier. Like whenever you see an address, you know that you have a contract, you have a piece of code backing it, which, again, makes reasoning about things easier. But it also allows us to lift many of the restrictions that we have that are inherent to schemes like 4337 from the verification phase. Because now this verification happens in the user device. So we can go completely wild when it comes to computing, to accessing whatever storage we need, to composing, to doing whatever we want as part of that verification, without fear of introducing a denial of service and any sort of attack vectors on the sequencer. Why? Because it's not the sequencer executing this. It's the user. The user runs this verification phase and just outputs a single CK snark that proves that it was correct, along, again, with a series of nodes, commitments, and nullifiers. And not just that, but we can also abstract fee payments in a much more interesting way. We can have here in green, we have what would be the verification phase of a transaction, in which the user sends a request, the account contract takes care of authorizing it using whatever cryptographic scheme the user wants, and sends a request to, let's say, a paymaster contract that takes care of outputting a node, outputting a commitment that is going to have the payment for the sequencer, for whoever includes this transaction on the network. And once this verification phase is finished, sure, we go along with an execution phase. All of this happens within the user device, again. So the only thing that the network sees that lives in the mempool is the snark of private execution, along with the set of nodes, commitments, and nullifiers. And the important thing here is that one of those nodes is a node meant for the sequencer to pay for their services. But we can take this one step further. In particular, when we're dealing with private state, we often have the need to send private information to a recipient, which means we need to encrypt it. And having each account being a contract allows us to define which methods of encryption we want for each of the recipients, for each user. So if I need to send encrypted information to someone else, I can actually query their smart contract, ask, hey, how do you want this information encrypted? It may not seem that interesting when it comes to encryption. Encryption is pretty much a solved problem, quote unquote. But when it comes to node tagging, it becomes much more interesting. By node tagging, I mean the ability to being able to find across the whole sea of encrypted information that the network outputs what particular pieces of data are relevant to the current user. And we have been exploring many, many different cryptographic techniques for that, OMR, private sector intersection, private information retrieval, hell, brute force even. And the main conclusion is it's definitely an active area of research. So by abstracting it away from the protocol, we encourage wallet developers, we encourage researchers to explore new techniques that will get built into the different account contracts, the different wallets, and allow for rapid experimentation without having to fall into a protocol upgrade every time we want to make an improvement to any of these techniques. But we can use these new patterns not just for improving on specific things to the private network, but also for improving on more traditional patterns, such as ERC20-like approvals. ERC20 approvals suffer from a number of known issues, mostly related to usability and security, like requiring extra transaction or application setting maximum approvals for the sake of saving gas. There are a couple of patterns, such as permit or permit2, that alleviate some of this, but still it's worth exploring what happens if we move into a situation in which everything is a contract. And actually the solution turns out to be stupidly simple. If you want an application to carry out an action on behalf of a user, we just ask the user. And because the user, again, is a contract. So a typical flow for, let's say, calling a swap on an exchange contract where the exchange needs to trigger a transfer on behalf of a user, turns out that the token contract only needs to ask the account contract, hey, is this transfer authorized? And you can provide to the account contract as much contextual information as needed so that the account contract can decide whether to authorize that or not. And even more, when these kind of authorizations happen locally on the user device and the authorizer is also the transaction sender, which again happens in most of the scenarios, we have access to this private execution oracle. We have direct access from the contract to wallet software that can interactively ask the user for permission to carry out that action. So we don't need to set up an authorization payload or a pre-signed message or set up an initial allowance before executing any of the flows. We can just trigger whatever actions we want, and whenever an authorization is needed, then that authorization will get funneled into the user wallet and for the user to respond, which makes both reasoning about these authorizations and implementing UX improvements a lot easier. So to sum up a little bit, now that we have gone through all these topics, what we have seen is that what we have presented is what we're currently designing. This is all in flux. We keep doing improvements. We keep changing our design. I actually had to change a couple of the slides 2 days ago based on recent conversations. But the point is, all these discussions are happening in public, happening in our forum. So I encourage you to join in, to join the discussion, to share your ideas, to challenge what we have presented with the spirit of not just improving the design for the Aztec network that we're building, but also generating new learnings that can be picked up by other networks, including the Ethereum network that we all know and love. Thank you. Okay, I think there's time for questions.
Any questions?
It's too early. Oh.
We've got one down here.
Thank you, random stranger.
Will the Aztec network have token approvals then, based off the flow you just went through?
We'll have what?
Just to clarify, the Aztec network, will it have token approvals for when you're using apps? Will I have to approve USDC to use it?
Yeah, basically following this flow. Yes, the idea is to build this sort of flow into any sort of token standards, even though token standards are not yet finalized, but we already have proof of concept in our repo about this. Yeah. Thank you for your question.
Any more questions?
Yeah, I just wanted to ask very briefly about nodes and how would the node, like what would nodes look like? What would be running a node look like on Aztec? Is there anything specific about it or anything unique?
So if I heard correctly, you're asking about nodes and how they get broadcasted through the network?
Yeah, anything about the node implementation that's interesting.
Oh, yeah. So there are two things to distinguish here, right? Like one of it is the specific node implementation, like what's in a node, and that's customizable by each contract. Like the token contract, for sure, will have a node that represents value, but you can represent any sort of arbitrary state in a node, and we allow contract developers to define the shape of nodes however they see fit. So a contract can output nodes that have value, that have strings, that have identifiers, that have any sort of information, and also nodes that generate nullifiers in any way. That's one thing. The other thing is broadcasting the nodes. Basically, when you want to send information in the form of a node to another user, you can either do it off-chain via private channel, or the contract can force that node to be broadcasted to all one and included to guarantee that the recipient will be able to see that node. That node gets encrypted according to a scheme requested by the recipient. And the thing that we're currently researching is how that node gets tagged so that the recipient knows that that node, among all the nodes published, belongs to them without other people knowing that. And also allowing them to query and to basically request the specific nodes that are meant to them, let's say to a third-party service, without disclosing which those are. And that's where things get interesting. You should probably talk to that guy about it.
Okay. Thank you very much, Santiago.